In this video, we're going to use the Lagrangian technique to analyze the labor-leisure choice model. A person's utility function is given by the following. C is consumption spending. L represents hours of leisure. H is going to represent hours of work. And we're going to assume this person has 16 hours a day available for work and leisure. 8 hours is going to be reserved for sleeping. Therefore, 16 will equal H plus L, and it'll be convenient for us to solve this for H. H equals 16 minus L. Hours of work equals 16 minus hours of leisure. This person's market wage is $10, so the person's consumption spending will equal the wage times hours of work. We're going to assume that this person has no non-labor income in this example. So substituting in for W, consumption spending equals 10 times hours of work. And the next thing we're going to do, another substitution, hours of work is just 16 minus L, so I'm going to plug that in over here and then simplify. This gives us the person's budget constraint. Consumption equals 160 minus 10 times L, where L is hours of leisure. So we're ready to maximize utility. We're going to set up our Lagrangian here. Our utility function, our objective function is here, and we're going to maximize our objective function subject to the constraint. Now, what I have in parentheses here, how did I get that? So we have this consumption constraint over here, this budget constraint. I'm just moving everything from the right-hand side over to the left-hand side, so subtracting 160 from both sides. And then I also have to add 10L to both sides, so that's why we have a plus 10L. Minus 10L, I have to add 10L to both sides to move it over. Now taking some partial derivatives, taking the partial derivative of the Lagrangian with respect to C, we get this result. This 0.5 on the C term comes down in front, and then 0.5 minus 1 leaves us C raised to the minus 0.5 power. Nothing happens with the L term here. And then don't forget lambda is touching C or is being multiplied by C. So the derivative or partial derivative of C times lambda is just lambda. Set that derivative equal to 0. Another partial derivative, the Lagrangian now. We're going to take the Lagrangian here and going to take the partial derivative of it with respect to L. What we have on L up here in the exponent, we're going to bring down in front. And then 0.5 minus 1 leaves us L raised to the minus 0.5 power. And don't forget, we have lambda being multiplied by 10L over here. We don't have to worry in this case about lambda times C. That's just a constant treated as 0. When we take the partial derivative and then lambda times minus 160, that's just another constant which will be treated as 0. So lambda times 10L. The derivative of that with respect to L is just going to be lambda times 10. Setting that equal to 0. And then finally, here's our last partial derivative. We'll just get back what's in parentheses, setting that equal to 0. The next step is we're going to take those first two partial derivative results that I'm rewriting here and solve them for lambda. So moving this 0.5 times the C stuff over to the other side, lambda will equal this. And then likewise over here, moving this 0.5C times L stuff over to the other side, lambda times 10 equals this. Dividing through by 10 gives us this result. Minus 0.5 divided by 10 is just minus 1 over 20. The next step is we're going to set these two lambda equations equal to each other. Here again are our lambda equations from the last slide. Set lambda equal to lambda. Making our substitutions. You'll notice that the minuses will cancel here. And then let's multiply everything through by 20. So 20 times 0.5 is 10. Again, the minuses cancel, so they're missing. Following the rules of exponents, on the left-hand side, the C to the minus 0.5 power, we can move into the denominator. And then on the right-hand side, L raised to the minus 0.5 can also be moved into the denominator like this. And then if we multiply through by L to the 0.5 power and multiply through by c to the 0.5 power. You'll just get this nice result that c equals 10 times L. We're going to plug this into the constraint, our budget constraint. So where I have C in the budget constraint, I'm just going to put 10L, as I've written up here. Solving this for L, adding 10L to both sides, and dividing through by 20. This person will take 8 hours of leisure. That means this person's consumption is going to be C equals 10 times L. What is L? 8. This person will be able to afford $80 of consumption spending. Hours of work is 16 minus L. So this person has 16 hours to allocate between work and leisure. This person will spend half the day in leisure and the other half of their 16 hours, I should say, in work. And that is the end. I hope you found this video helpful.